Hello. Now in this session today we'll see what is critical or whirling speed of a shaft. Now this is basically a transverse vibration or transverse displacement of a shaft. So let us say there is a shaft which is say mounted on a bearing, and for example say there is some rotor, maybe some flywheel or a pulley on this shaft, and this is rotating at certain angular velocity or speed, say omega, and this is having some mass m. Now what happens is, when this is rotating at a greater speed, it is observed that at certain speed this shaft starts vibrating very violently in the transverse direction. Now that particular speed at which this vibration is very violent is called as the critical speed or the whirling speed of the shaft. That means what is happening at that condition is that the amplitude of the vibration is too great. So now let us say see this situation. See what happens is, say when I am saying there is some rotor, not necessarily this rotor, the CG of the rotor is at the center or the axis of rotation. It is eccentric, right? So let us say it is having some eccentricity, if I say so, having some eccentricity E. Now what happens is, when this starts rotating, so there will be a centrifugal force, right? There will be a centrifugal force acting radially outward. So what it will do is, it will sag the shaft like this. So the shaft is going to bend. So that means this CG will be furthermore away from the axis of rotation. So if we see the condition that way, so it is the same shaft, if I say, so this is the bearing position, and say this is the supposed to be axis of rotation, which is horizontal. So what is happening is, the shaft bends like this. So I am showing a very exaggerated form, and say this is what the condition of the rotor is. So, and the CG of the shaft is somewhere here, if I say. So this is, say I name this point as G. So you may see that this is the eccentricity of that CG, which is E, and this displacement, additional displacement in the transverse direction, say let us say this is Y. So maybe now if we see the considerations, let K be the this shaft is having some stiffness, right? So let us say it is the stiffness of the shaft, right? And we have said E is the eccentricity, so there is E which is eccentricity, so it is the distance of CG from axis of rotation, and Y is the additional displacement, right? It is the additional displacement of what? Displacement of the CG from the axis of rotation, we can say, and this is happening due to centrifugal force. Right? So this is the condition, and say this is having some mass m, and as I said, omega is the angular speed of the shaft, and there is additional term I will use here, which is omega c, and I'll call this as the whirling speed or the critical speed of the shaft. Right? So now if we see the centrifugal force which is causing the deflection, so if I say centrifugal force which is causing the deflection, what will be equal to? We say that it is m omega square r, right? So we say that the magnitude will be m omega square, where omega is the speed, r. Now what is this r? Now this r, if you see in the diagram, now this will be the actual displacement from the axis of rotation. So this is r. So r is equal to, in our case, we will see this r is equal to y plus e, right? So that means my expression becomes m omega square y plus e. So this is that r. So now when this is getting deflected, let us say what is this stiffness. So it is going to restore. So there will be a restoration here, right? So restoration will be in the opposite direction. So this restoring force, we can say, or the force which is resisting the deflection. So I can say force resisting deflection, right? This will be simply the stiffness into the deflection, and deflection here is y, right? And therefore I can say for dynamic equilibrium of the system, I can say this resisting force will be equal to, so the dynamic equilibrium of the system will be what? When these two are equal. So I can say k into y is equal to m omega square y plus e. So we can say ky is equal to m omega square y plus m omega square e. So that means ky minus m omega square y is equal to m omega square e. So I can say that, so if I take y common, so y will be equal to m omega square e upon k minus m omega square, right? So if I divide this equation, so if I show it here, so if I divide this equation by this term, so what we will get? So we get y is equal to, can say, e upon m omega square minus 1. So if you see, have a look at this term k by m. right? We have studied the basic equation of vibration. There we have understood. Now this is going to vibrate. Transverse vibration will be in this fashion. So k by m, under root k by m is the natural frequency, right? So that means I can say this is E upon k by m is omega n. So this omega n, whatever natural frequency of the system, I can say that this omega is the critical speed, right? Under root, so that means it is omega c square upon omega square minus 1. So I can write it this way as E upon omega c upon omega square minus 1, where we can say this critical speed, which is the natural frequency of vibration at this situation, and this can be definitely under root static, we know the static deflection, so g by delta, or which is under root of k by m. This is known to us, right? So that is how we can express this situation. So now when we further simplify it, so we have seen that this y came out to be E upon omega c upon omega square minus 1, right? So I can express this expression as the ratio of these two displacements, y by E, to be equal to 1 upon omega c upon omega square minus 1. Now if I take out omega c, I can write it mathematically this way as 1 upon omega c upon omega square. If I take it out common, so it will be 1 minus 1 upon omega c upon omega square, right? This is just mathematically we are trying to express it. So I can get this y by E to be equal to, so if I take it to the numerator, so it will be omega upon omega c upon 1 minus, now if I take this to the numerator, so again this becomes omega upon omega c square. So this was square, so I get the expression to be like this, right? So, or again I can express this same expression as y to be equal to omega upon omega c square into E upon 1 minus omega upon omega c square. So why we are doing this is to understand the situation. Now you will see this is the omega is the speed of the shaft and omega c is the natural frequency. Now if we see that this omega is equal to the omega c, which is equal to the natural frequency, so what will happen? At this speed, resonance will occur, right? So when the resonance is there, so when this resonance occurs, so what is going to happen? The amplitude is going to increase tremendously, right? So this speed, so we can say when this speed of the shaft is equal to the natural frequency, right? So this speed is called as the critical speed of the shaft. So what is happening in this at this situation is the system is going to vibrate very violently. So this will be called as the critical speed, or it is also called as the whirling speed of the shaft. Sometimes it is also called as the whooping speed of the shaft. So that is how we understand it, right? So so we can say that the y value of y is positive below the critical speed and negative for the speeds greater than omega n. That means if you see that when this omega is less than omega n, we will get the y to be as a positive value, right? And when we see that this omega is greater than the omega n, in that case we will get this y value to be as the negative value. So that means when it is positive, so as if you can say for this condition, when omega is less than, so when this is rotating, so this is center of rotation, let us say, or say this is the axis of rotation passing. So this S, we get this displacement as positive, and this is supposed to be the eccentricity, right? So from the rotation. So this is the condition when this is negative, and when this is positive, and right. So that is how we interpret the situations. Right. So this is all in this session.